Okay, so welcome to the Spring Working Group.
Turn on the mic.
Good afternoon. Welcome to the Spring Working Group. We have a full agenda, so we'll start right on time. So this is the usual note well, but it's still important every time. So you should read it and agree with that. This is a few tips for the meetings, both if you're in line or in remote or in person. For the for in-person participants, so if you are in the room, you need to log in to be part of the blue sheet. You also need to click before going to the queue, to the mic queue. And finally, you need to wear your mask. And if you're a remote participant, please shut down your mic if you don't need to speak. And don't forget to enable it when you need to. So minutes are being taken by Drew. Thank you, Drew. You're welcome to contribute, everyone, at least to correct your statements or name, but also to help take the minutes. Thank you. In terms of personnel, we have lots of change this week. Jim Gishar has been selected as a new routing AD. So congratulations, Jim. Starting this evening, I believe. So as a consequence, he will also step down as a Spring working chair, starting this week, this evening, I believe. Okay. So thank you very much, Jim. It has been a pleasure. Thank you for your work. It happens you will be also the new responsible AD for Spring, so you will keep working on Spring. Andrew, thank you very much for your contribution, your help and your support. And welcome, Jim. Alvaro will be appointing as the new chair. Welcome, Alvaro. It will be a pleasure. And starting this evening, I believe. So thank you. Reminding that the meeting time is quite limited, so we started on time, but still we only have 2 hours. And for this specific meeting, we had a request for more than 4 hours. So obviously, some requests are not part of the agenda. For information, we give priority to first working group documents, which has been discussed on the list, then working group documents, needed discussions with high interaction, and then other documents discussed on the list. So we would like to suggest all authors to start a discussion on the list or on their draft, to introduce it with a short elevator pitch, to ask questions to the working group, and to engage with the working group on the mailing list. It will increase the chance to get a slot if we have that kind of limitations. In terms of document status, we ran an adoption call for segment routing header encapsulation for alternate marking method. Time for comments has elapsed, but on-shares are evaluating the comments. This is related to the next question. So there is a question between using DOH, IPv6 DOH, or SRv6 SRH TLVs. And the point is that some data could be defined in both containers. And so we initiated a discussion on the mailing list. Thank you very much to all people who contributed. We would like ideally more feedbacks, so please have a look. So we gave a current summary, which is if the data is SRv6 specific, it should rather be in SRH TLV. Because the space is limited in DOH and it should be reserved for generic IPv6 capabilities. And second point is that it's in general better to avoid duplication. so in both SRH and DOH, because this leads to issues and complexities. If you have a short comment on the mic, you're welcome to. Otherwise, please comment on the list. Yes, Giuseppe?
Hello, can you hear me, Bruno?
Perfectly.
Yeah, I just want to add in this regard that during the adoption call, there was also a suggestion maybe from Greg to, in the short term, to consider the proposal of SRH-TLV as experimental. Maybe this is a viable solution in the short term before clarifying maybe what is the best between the encapsulation header, extension header, and SRH-TLV. So I just want to add this consideration regarding the adoption call of the alternate marking method.
Yes, I believe the comments has been sent on the list already. Yes, it's a good point.
Yeah.
We will consider it.
Okay.
In terms of documents submitted to ISG, we have a new document, which is SR application segment for multi-point service delivery, which has just been sent to ISG. And we also have two other documents, which is LSH integration and for service chaining and pass segment in MPLS base segment routing. So this is the agenda for today. The agenda is a bit short and the characters are a bit small also. Any comments on the agenda, any agenda batching before we start? No, if so, we'll start with Wemo. And for all speakers, please stick to your allocated time, which include both presentation time and discussion time. Thank you.
Hi, can you hear me? Good. Hello, everyone. Today, I'm going to talk about SR fixed path egress protection. Next page. First, I would like to thank all these people who give valuable comments and suggestions. So, in fact, this document is in the RTGWG working group. About 1 year ago, we request for last call, but we'll suggest to get comments from the related working groups, such as Spring and LSR. So 1 year ago, I sent a request for comments in the Spring group list, but don't get any comments. And recently, I also sent a request again and then get some comments. So before this one, we presented in the LSR, we get a comment and we address the comments from LSR. Right now, I would present this protection functions to get more comments from this working group. So this update version, we already addressed the comments just get from the mailing list. So basically, we update document to give more detailed descriptions about the backup path computation, and also added some tags regarding to some slow convergence, because in the network, some of those convergence slow, some those converge faster, and then we add some tags about that one. So in the following slides, I'll talk about egress protection mechanisms. Next page. So in order to provide egress protection, at first we needed some preparations. So here from this example, we have a path from ingress PE1 to egress PEA. So in order to provide protection for the egress PEA, we should select a backup egress. Here we select PEB to protect PEA. At first, we should configure these protections, such as we protect PEA using PEB and also the mirror seed. After this configuration, the backup egress node will create a forwarding table for egress node PEA. This forwarding table will be identified by the mirror seed. Mirror seed acts as a context label. In this forwarding table will contain the forwarding entry for the seed on the egress node. So that each entry for this forwarding table context for the egress node, the behaviors should be the same as on the egress node. For example, here we just give one seed, seed A. So after receiving a package with seed A on egress node will send the package to, for example, CE. And then the forwarding entry for the on the backup egress node will do the same thing. So after receiving a package with seed A, and then that package will deliver to the same CE. In addition to that, the backup protection information will also distribute in the network. After P1 as a PLR receive this protection information, it will compute the backup path and then create a forward entry for protections. So after this preparation, and then we are ready to provide protections. Next page. So here, when egress node PEA fails, P1 as a PLR will detect that failure, and then it will switch it will encap the package from that path, that SRv6 path. This encapsulation will using the mirror seed in addition to the repair list. This package, encap package, will deliver to the backup egress node PEB. When PEB receives this package, so the top seed will be mirror seed. Backup egress will get that mirror seed and then decap the package using that mirror seed as a context label to get the forwarding table for egress node PEA. And then using the top seed of the package and the forwarding table for the PEA to deliver the package to the same CE. So that's the mechanism for egress protection in action. So next page. So we would like to get comments regarding to this protection.
Okay, so next steps then, the chairs obviously encourage people to go and read the document if they have some cycles, and provide some feedback directly on the mailing list would be very helpful. I know this is a piece of work that Waymo has spent a lot of time on, so it would be nice to get some feedback, good or bad. Thanks, Waymo.
Okay, thank you.
Yep.
Next one also.
Who do we have next? Oh, you're next up as well?
Also.
Oh, okay. Popular today.
So this draft is about SRv6 path midpoint protection. Next page. So this draft, we send a request for comments to multiple lists. And then we get lots of comments, and then we summarize the question and our response. Also, we send those summarized the question and answers to the list. So we'll not talk about in detail here. So today I'll talk about the midpoint protection mechanisms. Also would like to get comments. So in fact, we already have midpoint protections. That's the existing one. But the existing midpoint protection can only work after failure until IGP convergence. But after IGP convergence on the failure, the current midpoint protection doesn't work. So that's why we propose some enhancement to support midpoint protection after IGP convergence. So let's look the existing midpoint protection first. Next page. So here, we suppose we have a path which is from node A to node P1, and then to node N, to node Q1, and to node C. Here, this is a path with some loose hope. In this path, we have an endpoint. So here in this path, endpoint is node A, node P1, node N, node Q1, and node C. So here, for the path will be encoded or represented by the end node seed. So here, for simplicity, we just use B followed by the name of the node as a end seed of that node. After receiving a package from CE, the ingress node A will encap the package with a segment routing header. That segment routing header will contain the seed list encoding the path. Then the ingress node will send the package to the next hop, and then the package will be sent along the path. So here we can see that the package will send from A to P1, and then P1, because the top seed is end seed of P1, P1 will pop that seed and then send the package to the next seed. So that according to the forward entry, the next seed is a node seed of N, so that is a loose hop, and then P1 will send the package along the shortest path to node N. So here, the package will follow 1, 2, 3, 4, 5, 6. That package will go along that way in the normal operation without failure. So when node N fails, P3 as a PLR will detect the failure. P3 will do the existing FR, such as TI-LFA, and then we'll send the package to the next seed around the failure point, around the failure node. So here is that P3 as a PLR will encap the package using a segment routing header. This segment routing header will contain the backup path. So here, the backup path is just a simple one, just contain node 1, node seed of node 1, and then the package will get around the failure point at node N, and then along the backup path to Q1, and then the package will get to the destination. So this is the existing midpoint protection, but this protection can only work until IGP convergence. After IGP converges, and then the package will not reach to P3 as a PLR, and then the package will drop. So let's look at the next page. We can see the exact behavior, why the existing midpoint protection doesn't work. Next page. So we can see that after IGP convergence on the failure of node N, and then on node A and the node P1, those nodes will not have routes to the node N. So in this case, after the node A, ingress node, receive packet from CE, A will still encap the package using a segment route header contains the path. So node A will send that package to node P1. After P1 receives the package, the top seat is node P1's end seat. So node P1 will pop that seat. So the like seat is the seat of node N. Because IGP already converged on the failure of node N, and then node P1 have no routes to node N. So in this case, P1 will drop the package. So that's the existing case. So in order to provide protection after IGP converges, so the way, or the proposal is that when node P1 has no routes to a failed node, such as N here, node P1 will get the next end seat to the destination DA, and then just forward the package to the DA, which is the next end seat after the failed node, and then along the shortest path. So here, for example, we suppose the shortest path from P1 to the next seat Q1 is along the green path here to P4, and then N1 to Q1. So in this case, we can see that this solution is simple, just that any node, upstream node, which is not like hop, which is not direct neighbor of a failed node, it will check whether there's a route to the failed node. If there's no route to failed node, we just get the next seat and then forward the package to the next seat along the shortest path. So next page. Yeah, we also, because this draft is submitted to the RTGWG long time ago, so the RTGWG working group also asked us to present this draft to the Spring group, and would like to get the comments from all of you, and then to help us to improve the draft. So any comments, and welcome.
Okay. I do have one comment. As you know, we have a Reddit document in the Spring Working Group to do midpoint protection for SRMPLS. Yeah, okay. So my question is, why do you think it would be better to address the SRv6 part in a different working group compared to have the two data plane in the same working group?
Well, I don't, because this draft is, first order is not me, and I think the first order they submitted to the RTGWG. You mean why we sent to the different group, right?
Yes, why?
Yeah, I think Zibo is the first order. I think the reason is that the reason may be some draft sent to the RTGWG and some draft to the Spring. I think as you suggest, it's better to the same working group because they similar.
This is the same problem.
The problem is at high level is same, but the
data plane is different.
Yeah, but different because one is for SR-MPLS, one is for SRv6. So high level is same, but in detail is different because in the SR-MPLS, and then we can change the stack. But for SRv6, we cannot touch the stack. We can only use the in-cap or whatever. So that's the trick there.
I understand the need for two different solutions. But in my opinion, if this is the same problem, it's probably easier to address in the same working group to have consistent feedback. And if possible.
Yeah, I agree. I think maybe it's because it's the same problem and then in the same group, and also maybe merge and then have one draft and then just have subsections, one for SR-MPLS and one for SRv6. That's also possible. Yeah, that depends on the other people's opinion. Yeah, I'm open.
So I have two people on the queue. I'm going to if you don't mind, Lewis, I'm going to jump you first because Yingxing, I see, is also there, and she's one of the chairs of RTGWG. So I'm assuming you wanted to comment from that perspective, Yingxing. So go ahead.
Hi, this is Ying Zhen speaking as RTGWG chair, co-chair. So I do for RTGWG, as RTGWG, we do aware there is a.
Can you get closer to the mic? Sorry, you have to kind of almost kiss it to.
Can you hear me?
There you
Yeah.
go. Yep.
Okay. So RTGWG does aware the existence of the MPLS solution in Spring. That's why we want to bring this work to the attention of Spring. And I think ideally we should, because it's essentially the same problem, right? We should merge the solutions somehow, whether it's different draft or at least the behavior should be consistent in a certain way.
Mhm.
Yeah.
Yeah, I agree. As at high level, is same, but just detail different.
Well, we can figure that out, but let's get some comments on the document on the mailing list for sure. Lewis.
Yeah, Louis from Juniper Networks. So I think if I'm not wrong, in this P1 operation, the P1 router, we'll drop the first label BN, right? If I'm not wrong, and then forward to BQ1. Am I correct? I mean, in this slides, right? P1 is doing actually the dropping of the first, the top one, right? The SID.
Yeah, the SID for the failed node N.
Yes. I think this is how it works. But the problem actually, if the N is the ABR or the border routers, P1 have no reachability to Q maybe, right? That is a problem maybe. That means the reachability from P to Q, because it must be go for N. That's a case, right? So it's dropping that one, still have a kind of loophole from my perspective.
Yeah, here, this is for middle point protection. So that means the N is the middle point, is not a ABR or edge node. So for edge node, and then that's a egress protection, right? So this the domain of this one is for middle point protection. That means node N failed is a middle node, is not edge node.
Oh, okay, I got you. So you have egress protection is the ABR in this case, right?
Yeah, that's right.
Okay, that's different approach. Right? Okay, thank you.
Himanshu.
Himanshu from Siena. I have a question. So you're going down the stack and going to the next hop. Now this stack was created for some intent, right? Does the P1 know what was the intent to switch to go to Q1 on a bypass?
Well, this one, so P1, just to check the top seed.
Right, I got
whether
that
it's
part.
reachable or not reachable. So what the semantics of that one, he don't know. he don't care.
But it doesn't preserve the intent of why the head end had created that SID list, right? Let's say it was based on latency or something that you don't have that information.
No, I don't have that information
Yeah.
right now. You maybe consider in the future to,
Yeah,
to
you should.
consider those kind of intent or whatever surface or related something. Yes.
Right.
Okay, speaking as a working group member, this one is a technical question. So for P1 to realize there is a failure on node N, so that will only happen after ICP convergence, right?
Yeah, P1 is a remote node. It's not directly connected to the failed node.
Right.
So P1 just check whether there's a router to that node to the top seed. He don't know there's a failure, or is independent of the failures.
Then how do P1 how does P1 know when to jump the pointer?
Oh, that's a good question. So P1 will check the forwarding table whether there's a forwarding entry for the destination.
So,
which is end seed of node of a failed node
so
N.
in this specific case, and the forwarding table to reach node N will only disappear after ICP convergence.
Yes.
So this only works after ICP convergence.
Yeah, after IGP convergence. No, this also works for the before IGP convergence and after IGP convergence. So before IGP convergence, node P1, there's a forwarding entry to node N. So node P1 will send the package along the shortest path to node N. So the shortest path is through P3. So node P1 will send the package to P3. So P3 is directly connected to node N. So P3 will detect the failure of node N. So P3 will do the normal FRR. So that's a before IGP convergence. So before IGP convergence, the package will be delivered by the PRR using existing midpoint protection. So after IGP convergence and then P1.
So that you are saying before convergence, you are using FRR
Yes,
instead
yes.
of what you are proposing.
Yes, yes, yes.
Okay.
Yes.
Lewis.
Sorry,
Please.
I just continued what the questions last. The problem actually, yes, to just say that N is ABL, you use another protection previous slides, right? But in this case, P1 do not have Q1's visibilities. Where do it send? You cannot send to P3, P4 because you don't know where to send. There's nothing in this routing table. Then how it descends? So this is the question you need to clarify how
so-
it works in this case.
So I've actually closed the queue because of just in fairness to other presenters, because we've got a really packed agenda. So I'm going to allow Shibo, if you want to answer a question, go ahead. Oh, and Shradha after that, and then we close, and then we can take it to the mailing list, which is good because this is exactly what we want.
Yes,
like
yes,
this
yes,
conversation.
Yeah, that's
So
good. Very good. Yes.
I'd like to see it go to the mailing list as well. But please go ahead.
Zibo from Huawei. Response for Louis. If the ABR is a fair node, ABR or SBR, because for SRv6 we usually enable inter-area or inter-domain routing. So if the ABR is failure, the middle point buffer it can work normally. Yeah. Thank you.
Okay. And
Yes, thank you, everyone.
Shradha, the question, last one, please.
Hello, can you hear me?
Yes, we can hear you. Go ahead.
Yeah, the comment is we have a working group document for SRMPLS for the same problem. And recently, based on the working group inputs, we've updated the solution to use near-site tunneling to solve this problem. I think SRv6, whatever this draft talks about, this would work for classic SIDs, but the micro SIDs also have a local, local SID. So which is also very similar to SRMPLS. So it would be better if all of these use a common solution rather than having different solutions for MPLS, SRv6, and SRv6 microsits.
Yeah, in this presentation, I just use a node seed as an example. In fact, in the draft, we also talk about adjacency protection. That's already included in the draft. As you said, yeah, both draft, one for SR MPLS, one for SRv6, at high level, they're same. The only difference in details.
Okay, I will go through the draft in detail and we'll comment on the list.
Yeah. Go to draft and any comments you can discuss on the list because the time is run out of time. Yeah, very good. You have comments. That's what I want.
Yeah, great. I'll let you ask a question because you've been stood there a while. So, but then we're done. So,
Sasha Weinstein. I just want to. I actually rather now have said exactly what I was going to to comment on. There is a similar draft for midpoint protection in a segment routing and PLS. I think that actually segment routing v6 is a bit simpler because all things are global there. So I think that the authors should try to provide a merged solution, because essentially most things here are exactly the same.
Yep.
And what Himanshu here said about the reason why the midpoint of a path shouldn't be bypassed also has been discussed with regard to Strata draft. There have been comments on that by Stuart, if I remember correctly. So I think it is the same problem. We should look for a unified solution for both data planes as much as possible. That's all.
Yeah, great. Thank you. Yeah, also regarding bypass, I will also add the text in the draft. Thank you.
Thanks, Sonia. Yep, good, good. Okay, next up is who? Liu Yang is next up.
Hello. Thank you,
Oui.
Mr. Chairman. Can you hear me?
Yes, we can hear you. Please go ahead.
Thank you. Thank you. Thank you.
Just let us know when you need us to move slides.
Okay. Thank you.
Yep.
This draft is about SRv6 underlay tunnel programming. Next slide, please. We have defined a set of SRv6 endpoint behaviors, but currently they don't consider the heterogeneous network segments under the IP layer. So this document we proposed to define a new SRv6 endpoint behavior, which can be used for the heterogeneous applications, especially the layer 1 channel programming. We called it NBXC. Thank you. Next slide, please. First, I want to introduce the program statement and the network requirements. The operator needs to deploy end-to-end SRv6 policy across network A and network B. For example, the network A is the metro and the network B is the core network, the backbone network. The forwarding nodes, maybe they may support both the layer 1 MTN FGO channel capability and the packet compatibility in the network A. But currently, these layer 1 channels are invisible to the end-to-end SRv6 controller, so they can't be directly programmed into the end-to-end SRv6 policy. Since the controller of network A has all the information about the bounding operation between end-to-end SRv6 policy and layer 1 channel, layer channel in this in this figure, we have the terms of MTN, which means the ITOT metro transport network. FGO means the MTN file granularity unit channel. So if we use a new SRv6 endpoint behavior, it can program the bounding behavior into SRv6 policies through the network. So the end nodes support both MTN and SRv6 of network A will execute this behavior and bounding and unbounding the end-to-end SRv6 policy to the layer 1 channel in PE1 and PE2 for uplink direction and downlink direction. Next slide, please. This behavior is associated with the underlay tunnel. Typical types of layer 1 channel include MTN and OTN. Others could be ended in the future. This end behavior can support argument to identify the different channel types and different ID spaces. Next slide, please. So it gives two cases. One case is end BXC behavior with argument. We extend the argument to encode the channel type and channel ID. when received a packet destined to S and is a local and BXC seed, it is processed by the following: get the channel type and channel ID from the lower bits of a seed and found channel X based on channel type and channel ID, and upload IP value IPv6 destination address with a segment list and forward the packet to the new destination wire channel, the layer 1 channel. The next case is end BSC behavior without argument. The seed is associated with the underlay channel and the process is replaced by the following to forward the packet to the new destination wire channel X. Next slide, please. In a typical application scenario, we use the NBSC seed and other types of seeds to build its segment list. In this figure, we give the typical example by using the NBSC for the P1 in the network A MTN network and in net B as our value V6 IP network. Next slide, please. For this application, we have implemented in the equipment, and China Mobile has successfully completed the field trial. In this year, we also successfully to test the orchestrator and to combine the end-to-end SRv6 parts, include the MTN network and IP network in the field trial. Next slide, please. That's all. Thank you, and comments are welcome for this draft. Thank you.
Okay, thank you. So a few people on the queue. Lewis, are you meant to be on the queue or not? Or did you not remove yourself before? Please remember to remove yourself from the queue once you've spoken. Sasha is up next, unless that's still there. No. Okay, Ran Chen, please go ahead. Okay, go on. Okay, no questions in the room, so we can move forward. So thank you.
Hello, can you hear me?
Yes, we can. Please go ahead.
Okay, I'm Yao Liu from ZTE, and this draft is about extending ICMP for IPv6 related information validation. Next slide, please. As we know, IPv6 addresses, especially SRv6 seeds, can be related with extra information such as VPN services, endpoint behaviors, flex idle service functions, and etc. And in MPLS and SRMPLS, MPLS labels can be related with various FEC information as well. Procedures for simple and efficient mechanism to verify the data plane against the control plane use MPLS LSP pin are well defined. Normally, when a new feature is introduced, the LSP pin is still applicable by defining new FEC subtier V with the new information encoding it. Compared with MPLS, there's no efficient mechanism to verify the data plane against control plane in IPv6 networks. And this draft attempts to fill the gap by defining new ICMPv6 messages. Next slide, please. And two new types of ICMPv6 messages are defined separately for validation request and validation reply. And in the validation request, one or more validation objects are included to carry the information to be verified. And in the validation reply, the code field indicates the validation result, such as validation path or malformed request received, or one or more of the objects were not understood, or information mismatch. Next slide. And this is the format of the validation information object in the request message. It follows the ICMP extension structure. A new class number is defined for the object, and the C type indicates the type of information carried in the object, payload that needs to be verified. Next slide. And following are some other structures of some typical object payloads. Most are defined taking examples by FEC subtheories in LCP. And the first is SRv6 endpoint behavior for SR network programming. And the next is IPv6 prefix IGP algorithm, and it's applicable for both SRv6 and regular IPv6 prefix. And next please. And this object is defined for SRv6 IGP adjacency. Next please. And the objects for VPN IPv4 and VPN IPv6 prefixes in SRv6 VPN services are also defined. Next, please. And here are the main processing procedures. Sending a validation request is kind of like pinging a SRv6 SID or IPv6 address. One or more validation information objects are included in the request. And the target IP means the IPv6 address to be verified. The validation request is sent with the target IP set as a destination address without SRH, or set as a last segment with SRH. All transit nodes will process the validation request message like any other normal IPv6 data packet. And the target node is a node receiving a validation request, while the destination address is locally configured as a segment or local interface. If the packet is well-formed, the target node verifies the information encoded in the validation information objects against the local information. And after validation, the target node must form a validation reply with the return code set based on the validation result, and the reply message is IP-routed. And on reception of a validation reply, the node should attempt to match up the reply with the request using the identifier and the sequence number. Next, please. Oh yeah, that's all. And because this draft is mostly related with SRv6, so we plan to present it in the spring first to address some interests and comments. And that's all.
Okay, thank you. No comments, no questions. Okay, let's move forward. Thank you.
Thank you.
So, hello everyone. This is Wei Changcheng from China Mobile, and so this draft provides a solution to distribute SRv6 located by DHCP. The draft have been presented in last two IETF meeting in the DHC working group, and we got a positive feedback, and the chair suggests us to present it in Spring working group because it's related to SRv6. So next page. So the background is that here the figure shows example of the operators metro network. So the CPE in those network may also need support IPv6. At that moment, we might have some issue. It's very large scale, even more than 50 kilometers, 50K nodes, and it's also wider geographical distribution. So we need some solution to optimize the provisioning. Here we would like to use the DHCP solution to assign the locator to the IPv6 endpoint. It can simplify the configuration, and it can also dynamic learn the IPv6 subnet routers. So it can help the maintenance team to improve their efficiency. Next page. So the proposal is very simple. You can consider if the IPv6 locator is a prefix, it's similar. So first step, the DHCP server allocate IPv6 locator as a prefix. And the second step, follow the DHCP PD process. And the third step, after the locator assigned successfully, such as BRAS, will dynamically issue the locator subnet route locally and distribute it also to the backbone. And the last step, when you want to release the locator prefix, you just need the BRAS to delete the locator subnet route. Next page. So in next page. Yeah. It can support the both original IPv6 seed and the compressed IPv6 seed. Next page. So we need a extension. We have some discussion in DHCP, the DHC working group, and we at firstly we need to define a identify association for IPv6 locator option. Next page. Based on that, we need to define the IA IPv6 locator option. So in the option, we can define the basic locator format, and it can carry the IPv6 locate. Next page. Yeah, so when we have the both extension, we will have this encapsulation format. It's like the other options in DHCP protocol. Next page. So here is two application scenario. The first application scenario, BRAS work as a DHCP PD server. It's very simple. And next page. The second scenario, BRAS can work as a DHCP relay agent. So it's also follow the previous basic DHCP processing. Next page. So currently we have a present the draft in DHCP working group, and we hope to get more comments from Spring working group. That's all.
I had one question, Wei Cheng.
Yeah.
Just in terms of your expectation, just from a cursory look at what you just described, it looked like the protocol work actually needs to be done in DHCP working group, correct?
Yes.
So
Yeah.
what you're really looking for is not to actually progress the document in Spring, but to get comment from the Spring working group. That's really what you're looking for. I just wanted to clarify that.
Yes. Chairs from DHC working group suggest us to present it here because they hope the expert here can review if the solution follows segment routing rule.
Yeah.
And,
Okay.
yeah.
I just want to make that clear. Timothy on the queue.
Yeah. Thank you.
Yeah, Tim Winters, DHCP Working Group Chair. Yeah, I mean, we did all the protocol work and the draft. We just wanted to make sure it was actually going to get use. That's really what DHCP wise, we've got all the bits, right? We've given them feedback. It's more of, is this going to be used? We don't want to use up options and do all that work.
We appreciate that. So, yeah, great.
Yeah. Thank you.
So getting review from people in the working group would be very helpful. Any more comments or questions?
The next draft is also.
Okay. Yep.
From,
Yep.
Yeah.
Okay. So we can move on from this one then.
Okay. So, okay. This draft is about the multi-homed egress protection. And this draft have been presented in last IETF meeting in RTG working group. And the chair from RTG working group suggests us to present it in Spring also because it will touch some seed list of SIV6. So that's why we applying the slot here. So next page. So why we develop this solution? Because we would like to provide the faster failover for the multi-home egress scenarios. And we hope it can be stateless and planning-free SIV6 egress protection, just like the principle of SIV6. So it's very simple. The first mechanism is that we need to carry a backup seed at the egress, at the head node for the egress protection. And then we need to define a new flavor. We call that penultimate segment decapsulation flavor to indicate the SIV6 penultimate segment decapsulation. So it's very simple. And next page. So here is the encapsulation of the backup seed. We just need to insert the backup seed to the segment left 0. So the top of the seed list, the last seed. And next page. And the PSD flavor is also very simple. It will be applied to such as n.dt4, n.dt6, and so on. It's also just need a very minor pseudo code change. We just need to add a condition for S02, you need to allow the segment the seed for the penultimate to ignore the condition. So that will running just at the egress node. Okay, next page. So here we give an example of the processing. For the ingress node, it's very simple. It's just need to insert a backup seed on the top of the seed list with the new flavor. And for the primary egress node, and when it receive a packet with the PSD flavor, it will decapsulation the packet and forward the inner packet as a function indicate. And for the penultimate endpoint, it just worked when the fail happen. So the failure happen. If it detect the reach to the egress node cannot work, and it will jump the seed to the backup and copy the backup seed to the destination address and then send the packet so that we can achieve the egress node protection. Next page. So compared to the last version, we add some new text, especially last meeting. There are comments about how the transit node handle the protection, and we narrow the scope. Now we hope the egress protection mechanism doesn't take effect on the transit node. We just cover the direction connection parameter node. And we also add some text to describe the penultimate endpoint to sense the primary egress node fault, such as IGP convergence, BFD detection, and some other physical layer alarm, something like that. Okay, next page. So we would like the people in Spring can review it, and any comments are welcomed. Okay.
Okay, thank you, Wei.
Thank you.
Okay, next is presenting.
Hello. Good afternoon, everyone. Okay, I'm Nangang from Huawei Technology. Next slide, please. This document is about the security considerations for segment routing version 6 networks. In the document, we try to give a complete view of the various for threats to the SR version 6 networks. And we also describe some basic solutions to address these threats. And some basic security policies are also provided in the related sections. And this document, segment routing may be used in different scenarios, and there may be many security considerations. So this document may help us to track these security threats and provide some guidance to the network operations. And it can also be used as a reference for the other segment routing documents. And we will continually maintain this document. Next slide, please. Currently, we included the main file threats, that is eavesdropping, falsification, identity spoofing, packet replay, and DDoS, and some basic solutions are also introduced. Next, please. Okay, we have maintained this document for several years from 2019, and we add many details about the solution and some figures to illustrate these solutions and threats. Recently, we added some descriptions on source address validation for segment routing version 6 networks. It can be used to do some identity prevent identity spoofing maybe, and also add some descriptions on DDoS mitigation tools. Next step, we will continue. We like to solicit comments from Spring Working Group, and we will continually maintain this draft. Hopefully, it will be helpful to us. And if it becomes stable, we'd like to request a working group adoption. Maybe any comments?
Yeah, one comment we had from the chair's perspective is that we've kind of wanted to encourage a security considerations document from the working group for quite some time, and I don't know whether this is the one, but it's certainly from the chairs, we'd definitely like people to review it, and we would like to get a document out from the working group that specifically addresses some of the security considerations. So again, encouraging people to really go read that, get involved, and try and improve that. I know Joel's got some specific comments in that area. He's not here. He had a conflict with a different thing that he had to do in another working group. So I'm sure he'll have some comments. So he'll probably put those on the mailing list and look out for those. So Andrew, please go ahead.
Yeah, Andrew here, Liquid Telecom, speaking strictly as a working group participant. I've got a number of issues with some of the things in this document. For one, in section 1, you state that SRv6 uses an SRH. That is not always true, and is a dangerous assumption. It's dangerous to put into the text, because there are many cases where an SRH is not applied. In section 3, you state that because everything runs in a trusted domain, there are problems in the trusted domain. That again makes a huge leap that everything in that trusted domain is going to remain trusted. And the same thing in sections 4.2 and 4.3, where you say at the start of those sections, packet falsification cannot happen within the trusted domain, yet you then go on to provide a solution for something that you've just said in the previous paragraph cannot happen. In section 4.3, you say identity falsification cannot happen, and again, the same thing. The fact is that these things can happen, even in the case of a trusted domain. If a Linux box on a network gets hacked, the Linux box can send whatever it likes as a v6 packet, straight out the stack, straight from userland. It's not hard. And while I think it is a very good thing to highlight the risks and potentially try and provide solutions to them, to make statements that these things can't happen because it's a trusted domain, it's simply not true. And I really like to see that refined so that we are providing a more clear and accurate picture without simply stating, well, these problems don't exist because of a trusted domain, because it's simply not accurate.
Yeah, thanks for your comment. Due to time limitation, let me try to answer your the second question briefly. We will add maybe we need to add more details in the draft. Actually, if we have trusted domain, there may be also some threats in the segment routing networks because some threats may come outside of the networks, and we need to do some policies as a boundary of the transmit domain networks. Of course, we'll carefully consider your considerations, maybe response to you carefully with more details. Thank you. Okay. And by the way, we also solicit the comments from Joe. He also give some
Yeah, I
comments.
think Joel will probably send you comments on the mailing
Yeah, I
list,
have
but-
received that.
Yeah,
Yeah,
okay.
thank you.
Good. Any other comments? Okay, so again, encourage people to go and read that and help to get something out from the working group in that area. There are several things I've noticed coming through from a security standpoint that clearly there's people wanting to put some focus in that area. So look out for those documents and please provide feedback to the authors. And I think it's some good piece of work that we can do. Okay, next one is, who's up for that? Shraddha, go ahead. You're
hello.
remote, I believe. Yep, we can hear you. Please go ahead.
Okay, so how do I move the slides? Just use the arrows. Is it?
Just say move slide and we will jump to your command.
Okay. Yeah, my name is Shraddha Hegde from Juniper Networks. I'm presenting updates to this problem statement for interdomain intent-aware routing using color on behalf of my co-authors. Some background on this draft. So this is a merged draft from the previous drafts in Spring Working Group, the seamless SR and the problem statement for BGP car. These two drafts getting merged, and this we're working on this merged draft. Next slide, please. Have you look at some of the updates from last version and next steps? Next slide, please. So we added service intent requirements. So basically, these requirements talk about the intent requirement as applied to CEP link as well. And it describes intents such as minimization of end-to-end metric, could be IGP metric or link cost. And another intent is inclusion of link affinity as applied to CEP links. There's also another set of service intent requirements for VNFs. So the VNFs deployed in the service layer, the transport isn't aware of these service chains. But the actual service prefix that is supposed to use these VNFs and the service chains are indicated using a color. Next slide, please. OEM requirements have also been added as part of the updates. So the basic requirement is to be able to support end-to-end ping and trace route for MPLS as well as SRv6 based on these base RFCs. Another requirement is the ability to validate a path inside a domain. And then requirements on counters that, on a per path and per color basis, you should be able to get counters on ingress of the path, transit, as well as egress. Next slide, please. We also did some minor updates based on comments received on the mailing list for per flow steering in the traffic steering requirement section. And there's also one new requirement added in the deployment requirement section for non-congruent color to intent mapping. Next slide, please. So we request the working group to review and provide inputs. We still have one small part of the work pending, which is the multicast requirements. The authors believe that the working group is, the document is ready for working group adoption. So any questions, comments?
No, nothing in the room. Okay, thank you.
Okay, thank you. The next one is also mine, I guess.
Oh, it's you as well. Okay. We're just bringing it up. Okay, please go ahead.
Yeah, so this draft is about auto edge protection. I'm presenting behalf of my co-authors. Next slide, please. So because of time limitation, I'll focus on the problem statement and why we are doing this and provide some concepts on the solution. The detailed solution can be referred to in the draft. Next slide, please. So the requirement here is to be able to achieve a 50 millisecond failover for the egress node or the PE node failure, as well as the PE-CE link failure. And the motivation is also to achieve, minimum configuration overheads in order to achieve this 50 millisecond failover. The idea is to automatically detect multi-homing and then build context so that and use that context for forwarding so that there is no special configuration required. Next slide, please. So we also looked at if what kind of applications would really require this 50 millisecond conversions. So some of the examples listed here, the content collection application for live streaming, and then real-time image-based applications, military application, as well as the financial trading applications. And there are also some operators who would want to provide premium service to some customers for this 50 millisecond failover end-to-end. Next slide, please. So this describes why we would need something called as context ID. So as seen in the diagram here, the PE3, PE4, and PE5 are the egress PEs. CE1 is connected to PE3 and PE4, whereas CE2 is connected to PE4 and PE5. So for CE1, PE4 is primary, PE3 is secondary, and for CE2, PE4 is primary and PE5 is secondary. So when PE1 is sending traffic to PE4, if PE4 goes down, then based on what service traffic it is, if it is CE2's traffic, then it is supposed to send to PE5. And if it is CE1's traffic, it is supposed to send to PE3. So because the P router is a transit router and is not aware of the services, there has to be some context to which the network is forwarding the data so that when the egress fails, the penultimate router, that is the P router, is aware of where to send. So here there is this context ID 30 and context ID 50. Context ID 30 is allocated for CE1, which is P3, P4 primary and P3 secondary, whereas context ID 50 is for PE4 and PE5. So when the traffic is being sent from PE1, it would use the context ID 30 if it is CE1's traffic, and it would use a context ID 50 if it is a CE2's traffic. And that's how P knows where to send the traffic. Next slide, please. So the idea of context ID and the egress protection framework has been defined by RFC 8679. So the basic concepts such as the context ID, that a pair of multi-homed PEs allocate same context ID. And if the primary PE is different, a new context ID would be needed. And also it defines what is a context table, wherein, when, the other PE, the secondary PE, uh, uh, constructs the context table like this. All the service labels that are allocated by primary PE would also be put in this context table in the secondary PE, so that when the protected traffic arrives, it knows where to send the traffic based on the service label that arrives in the packet. And then for this context label, RFC 8679 also defines the context label that identifies which table to use. So next slide, please. So given the background existing solutions and the problem statement, what we are trying to do is trying to automate this, so that the context configuration as well as the context label configuration and so on is not really required, because all this information can be derived based on the multi-homing advertisement, the BGP advertisements and detection of multi-homing. There's also another need for this automation. Many a times these services are virtualized and they run on compute servers, and they may be moving based on availability of memory and CPU. For example, a service instance that is using P4 as primary and P5 as secondary, it might move the service to another compute resource so that P3 becomes primary and P4 becomes backup and so on. So, manual configuration to handle this situation will be very difficult. So if we have an automated way of detecting this, it will be very operationally friendly. Next slide, please. So this I'm describing the concepts in the solution, not really describing the entire solution here because of the limited time. And I request people to go through the solution in the document. So here the basic concept is that there is some infrastructure pre-provisioning required. So this is similar to how anyone would allocate an anycast IP address or a node SID or a prefix SID. So in this case, it would require a context ID pool, which is an anycast address pool in case of MPLS underlay, and locator pool for SRv6 underlay. So this is one-time provisioning. And also for SR MPLS case, there will be an index space reserved on each node, which is participating in this auto edge protection. Next slide, please. Yeah, the second concept is detection of multi-homed prefixes. So when there is a service advertisement in BGP, the P3 and P4, let's take. So the P3 has received the same prefix from CE1, and it also receives the same prefix from PE4 via IBGP advertisement, and that kind of condition is used to detect the multi-homing of this prefix from between P3 and PE4. So the requirement is that to participate in auto edge protection is that they should all have this pre-provisioned anycast address pools and index pools, and they should not conflict between each other. So if that condition is satisfied, then P3 and P4 can participate in the auto edge protection. Next slide, please. So there is also this concept of context ID database. So we need to store which context ID is allocated for which multi-homed PE group. So when they automatically allocate the context IDs, each router store this context ID space, context ID to multi-homed PE mapping. And this mapping is built on both the primary as well as the secondary PEs. Next slide, please. Yeah, request more detailed solution for SRMPLS as well as SRv6 to be referred in the draft, and request review and comments. Any questions?
Okay, no questions in the room. I haven't seen anybody on the queue.
Thank you.
No, that's it. Thank you. Appreciate it. Okay, next. Okay, let's see.
Hello, this
Ben,
is Fu.
okay, so you're on the phone. Okay, please go ahead.
Okay, thank you. So this is Fu from China Mobile. I will present this this draft also with our co-author, that's from H3C colleague Chang Wanglin. So next page, please. So in SRv6, the destination address of tunnel can be VPN seed, and we propose using service seed as source address as well. That means for those services like L2 or L3 VPNs, we propose using VPN seed as source address rather than the interface address. So that only impact the VPN services. That is my intention. So once seed as source address, first on the next hop of the SRv6 tunnel headend, we can do source address spoof verification or validation by doing strict BRPF. Second, we on the tail end of the SRv6 tunnel propose introducing an SRv6 source verification table, which stores all of the authorized source address and the associated VPN. By doing this, we can filter out those unauthorized VPN access, allow only legal VPN traffic. So that's a basic idea. So next page, please. So there are several use cases. The use case one is for pass through the SR aware stateful firewall. The problem is SRv6 traffic will be dropped if there is a stateful firewall in the middle. This is because tunnel source address is interface address, but destination address is VPN seed. Thus, the forward and the backward traffic doesn't have symmetric source and destination address pair. So that's which is the basic requirement to pass through the firewall. So the traffic will get dropped. The solution is what we propose to using the VPN seed as source address that can make the source and destination address pair can be symmetric in both forward and backward direction. The second and third use cases are for overlay and underlay VPN services respectively. So the problem is even if SRv6 is in a limited domain, it deployed in limited domain, there still be risks for insecurity. For example, the software bug or some bad guys who can access the router and do some of the unauthorized configuration. In SRv6B mode, for example, in SRv6B mode, we can one person can illegally attack another's VPN easily by creating a packet with destination set to any VPN seed. In RFC 8754, specify each MAC to authenticate the SRH header. However, as I understand in the SRv6B mode, there is no SRH header, so there is that mechanism doesn't work. And even if there is SRH header, by doing the HMAC authentication, that is expensive because as far as I know, it's hard to reach the line rate forwarding. So the solution is to using seed as source address and having source verification table on tail end of the SRv6 tunnel. Then if there is a unauthorized access, packet will get dropped if the source address lookup is failed. So this solution will leverage the lookup ability of the router to enforce the VPN isolation. Please, next page, please. Once the source address is seed, so we need to consider what if there is a forwarding failure? ICMP packet will be generated if the destination is VPN seed. In this scenario, RFC 8986 suggests to allow upper layer header processing of types that do not result in packet being forwarded. Thus, the seed as source address will not introduce any new mechanism for OM handling, as far as I know. So that's my proposal. It's basically just for some security issues I can aware today. So that's all. Any questions?
There's a few more slides there. Doesn't want to go through those. Okay. Okay. No questions in the room. Thank you.
Thank you.
Yep. Certainly take questions on the mailing list as normal. Thank you. Jeffrey. Yep.
Hi, this is a new draft about SRv6 MPLS service interworking, focus on a new option. We call it option BC. Next slide, please. So there have been some drafts talking about interworking between SRv6 and MPLS. Some talks about transport interworking, and some talk about both transport and service interworking. In case of service interworking, we're talking about single plane PEs where the SRv6Ps don't even do MPLS over IP or MPLS over UDP. And so that means that there must be some dual plane interwork nodes that does the interworking. And there is an option A style where on the interwork node, there will be service instances that looks into the service header service traffic header to figure out how to forward traffic. Option B style is that the interworking nodes will allocate new service seeds or service labels when they advertise the received service route from one domain to another. And because of that, we need to maintain an per service label or per service seed forwarding states on the interworking node. Here, there is no option C because option C would mean that SRv6PE would have to do MPLS over IP or MPLS over UDP. Then that's just MPLS service all the way. Next slide, please. So this is one example of option B style. Let's say that SRv6PE1, it advertised 10,000 service prefixes, and they will use, let's say, 1,000 service seeds. For example, you have 1,000 VPNs. So, and you could have for each VPN you use a VRF table label. So those table labels, VRF table labels, will be embedded in the NRLI's label field, and with that you can just use one prefix, the same prefix seed attribute that includes a seed value and some sub-TLV, the seed structure sub-TLV to specify the offset and length of the locator, functional base, and argument base, and the transposition and offset and length. This will allow the ingress PE to superimpose that label that is in the NRLI to the seed that is in the prefix seed attribute. And with that, once you do that, you get the service seed to use to send traffic. Now, when that those routes reaches the interworking node, here's IWN. When the IWN, the interworking node, will re-advertise the MPLS sites with corresponding with 1,000 locally allocated service labels and create 1,000 MPLS forwarding entries to map the locally allocated service label to the individual SRv6 services. And notice that we're just talking about the routes received from one SRv6PE, and if you repeat that, you can get a lot of the forwarding entries on the interworking node. So, and the other direction is similar. So now the goal here is to reduce that 1,000 FIB entries, which is per PE, to just one entry. Next slide, please. These are the text that describes how it works, but I think we'll just skip to the next slide, look at the picture, and we'll explain. So this is the traffic, service traffic from the SRv6 side to the MPLS side. So the top part is the signaling. We have MPLS PE2 on the right side. It advertised the service prefix service 2 with label 200 in the NRLI, and with PE2 being the protocol next hop. Now, when the interworking node receives that route, it will re-advertise the same NRLI without changing the label field. It does change the next hop, protocol next hop to the IWN's loopback address, and it will add a prefix seed attribute. Inside this prefix seed attribute, there is a seed value, and the high part of the functional bits of the seed value will identify a new forwarding endpoint behavior corresponding to that particular next hop from which we receive the advertisement. In this case, is PE2. This new endpoint behavior, I'll explain it later when we get to the traffic forwarding part. So the routes is received, the route is received by the service SRv6 PE1, and then it will use the, according to the transposition offset and length, you will superimpose the label 200 onto the seed value. So then it will use that to send traffic. So if you look at lower left corner, I draw it out as that's the blue part is a locator of the interwork nodes plus the higher bits of the functional bits, followed by the label 200 that was superimposed according to the transposition offset. And then that is used to as the destination address and in the outer encapsulation to send the traffic. Notice that here, that's hfunc plus that 200, that is together is the functional bits of that SRv6 SID. Now the traffic arrives on the interworking nodes. That's high functional bits will identify endpoint behavior corresponding to the PE2. That endpoint behavior, we call it N.dbs, which stands for decapsulate, binding, and shifting. What it means that it would decapsulate the IPv6 encapsulation, and then it shifts or extract the label 200 from the SID itself, and then push that into the label stack as a service label. And that's endpoint behavior is also tied specifically to a PE. So from that, it will find out the node state for that PE2 there, or it could be another label if you're not doing the SR. The right-hand side could just pure MPLS without even doing SR MPLS. So as long as you use a label stack that can reach that PE2, you're all set. So the traffic is sent with that label stack, and then PE2 will just be able to handle it. So that's the direction from SRv6 side to MPLS side in terms of traffic. Next slide, please. This is the other direction. And again, I will skip the text and look at the picture. So here is the traffic is from MPLS side to the SRv6 side. If you look at the upper right corner, upper left corner, SRv6 PE1 advertised service prefix 1 with label 100 in the NRLI, and next hop being PE1 with a prefix SID attribute. Inside the attribute, there is a SID value, and there will be also be some transposition offset and length of those informations. And now the interworking node will re-advertise the routes without changing the label fields. It will use a new next hop. Here, I call it IWNH in the green color. That IWNH will map to the SID value in the received prefix attributes. If it's if it's IPv6 on the based MPLS on the right side, if it's IPv6, then that IWNH itself can just be the received SID value in the prefix SID attribute itself. And in addition, we advertise another transport routes. The prefix of that route is the IWNH itself. And then with a new label 300 there, and the next hop being the interworking node. Now, this route is the transport route, but it is advertised via BGP-LU, not by IGP. Now, those two routes arrive at the MPLS PE2. And PE2 will resolve the service route and then service routes the next hop and recursively. So eventually it will send traffic using label stack of the node seeds of the interworking node, followed by the label 300, and then followed by the label 100, that's being the service label. Now, the traffic arrives at interworking nodes, and it sees label 300. The label 300 is special. It's basically the binding label. It corresponds to the received seed value in the prefix seed attributes, and that also has a forwarding semantics, being that I'm going to pop that next service label in the stack and superimpose that popped service label here 100 onto the seed value that I have saved away before. Now, after that, it will use the resulting IPv6 address to send traffic to the SRv6 side. Next slide. Yes. Yeah. So this slide talks about the pros and cons of this approach. You can see that we have completely independent SRv6 or MPLS domains. One side is SRv6, the other side can be MPLS. It does not even have to be SR MPLS, just MPLS, pure MPLS. This will allow the incremental transition domain by domain. It also has option B advantages that you don't you can hide the topology of the other side. Now, notice that there is no per service seed or label state on the interwork node, so it has the option C advantage. And this also works with the EVPN label, ESI label based multi-homing procedure for split high-rising. The details are in the draft. It's pretty straightforward. This does require the interwork node to do something that special. Yeah. In one direction, it needs to extract lower functional bits and push that as a label. So when we send from traffic from SRv6 side to the MPLS side. In the other direction, we need to pop the next label and then superimpose that label into the SRv6 seed. So pros and cons, if it is important for the interwork node to save the forwarding state, this does work very well. And we were looking into the feasibility of ASICs. It looks like that it's very promising that some, not only in some vendors programmable chip can do this, but some merchant chips can also do this. So it's quite feasible. It all depends on if this is something that operators may be interested to deploy. Next slide, please. So obviously we appreciate the comments and suggestions. There are quite a few interworking drafts already, so we will figure out a plan to how to move forward with this if this is a good idea.
Okay. No comments in the room, so.
One comment, did you ask for a slot for base working group? Did you present at base working group?
Not yet.
Or maybe you should send an email to
Yes.
present the draft.
Yeah. Okay.
I have a comment, Yalo from ZTE.
Yep, please go ahead.
When we are, when we are deploying option B, the huge number of fib entry is a real problem. After reading this draft, and as mentioned by Jeffrey, the cons, usually we use the whole function part in the forwarding table, but in this draft, we use only the higher bit. It might be a challenge for the current router.
I'm having some trouble hearing very clearly.
Is it better now?
Yeah, better now. Yeah, you say that again.
Is it better now?
Please repeat the question.
Okay. Usually we use the whole function part when we in the forwarding table, and in this draft we use higher bits. So this might be a challenge for the current router, and another comment is that when the routes are re-advertised from the SRv6 domain to the MPS domain, and to achieve the goal in this draft, I think a certain seed allocation methods should be used. Because you can only put a different part in the 20 bits, because these parts will be translated to the VF table. We have labels in the MPS domain. So maybe some description or guidance about the seed allocation method can be added. That's all.
Okay, thanks. So for the first comments about just using the 5 high function bits, my understanding is that the way we handle SRv6 incoming SRv6 seed in the data plane is you just treat it as a IPv6 route. So if you install IPv6 routes with just locator plus the high functional bits with the corresponding the prefix length, and then it should just work. That's how I understand it. Now about advertising the seed or labels, in the drafts there it actually does talk about the situation where you may have more than 20 bits that you need to care about, and the draft does talk about how to address that problem. That's a detail. I will have to refer you to the drafts. And VRF table label, that was just an example. Now, when I talk about option B, it can be any kind of service label. It could be a prefix label or whatever label. Yeah.
Okay. No more questions. So we're going to be wrapping up a little bit early here. So you get early coffee 5 minutes before. So thank you for attending. That's a wrap.